Good evening and welcome everyone. My name is Stephen Shad and I'm the Executive Director of Communications at the Gerald D. Hines College of Architecture and Design. We are so glad that you are here with us this evening as tonight we continue our lecture series Matter Matters with our very own Andrew Cudless. Professor Cudless holds the college's Bill Kendall Memorial Professorship of Design Technologies and is the director of the new Advanced Media Technology Lab. The Bill Kendall Memorial Professorship was established in 2018 by the firm Kendall Heaton to honor the late Bill Kendall. Since its inception, the professorship endowment has grown to over $1 million with the generosity of Kendall's colleagues and friends, including the Hines family. The professorship provides funding each year in perpetuity that supports new research and engagement in design technology and materials. Today, following our presentation, there will be an opportunity for Q&A. Please enter your questions into the Q&A feature at the bottom of your Zoom window. Please note, questions addressed during the presentation that are entered into the Q&A window will not be addressed until the end of the presentation. And with all that said, I'm going to now turn it over to Professor Jeff Halstead, who will introduce Andrew. Jeff?
Great. Thank you, Stephen. Hello, everyone. Thank you for joining us. We're very excited to have Andrew Cudless here tonight at the Gerald D. Hines College of Architecture and Design. Before we begin, I want to take a brief moment to thank a few people who were integral in making this event possible. Dean Patricia Oliver, I'd like to thank you for your support in the program and your help in bringing Andrew to Houston. Thank you to the late Geraldine Hines and Barbara Hines for their incredible generosity to help fund the new media lab. Thank you to Dietmar Froelich, Stephen, and Trang Phan for their planning, organization, and technical acumen needed to coordinate and run tonight's lecture. Thank you, of course, to Andrew for taking the time to join us all here tonight to discuss your recent work. So I'd like to briefly introduce Andrew to all of you and to take a few minutes to talk about the theme of his lecture and the focus of his work. As you are all aware and excited, I'm sure, the school is set to debut the new Media and Technology Lab in which Andrew has been appointed to lead as the school's inaugural Bill Kendall Memorial Endowed Professor. Prior to his appointment here at U of H, Andrew was an associate professor at the California College of the Arts. It was here where I first met Andrew during an Architectural Association satellite conference that he ran and I attended 10 years ago. So this is a particularly meaningful event for me. I have been an admirer of Andrew's work for many years, and I'm especially grateful for the school giving me the opportunity to introduce Andrew to you all. So in 2004, Andrew founded Matsys, a design studio, exploring the emergent relationship between architecture, engineering, biology, and computation. The work of Matsys has been exhibited internationally and is in the permanent collections of the San Francisco Museum of Modern Art, the Centre Pompidou in Paris, the Frac Center in Orleans, France. His work on Confluence Park has won a number of awards, including a 2019 AIA National Honor Award. In 2019, he became the first American designer to contribute to Louis Vuitton Objects Nomad collection. He holds a Master of Arts in Emergent Technologies and Design from the Architectural Association of London and a Master of Architecture from Tulane University. In his lecture tonight, titled On Growth in Form, Andrew will discuss the work of his firm Matsys through 4 connected topics that reflect the way design is approached in his practice. First, Cudless will discuss the role of drawing in architectural design and production and its future in an age of automation. Second, he will describe his understanding of the material practice of architecture and its place in architectural education. Third, he will walk us through what it means to build solidarity with non-human life in architecture. And lastly, Andrew will conclude the lecture with a focus on the relationship between form, performance, and fabrication through an in-depth exploration of the design and construction process for his Confluence Park in San Antonio. In a recent Los Angeles Times article titled, "Who's the Man Behind Louis Vuitton's Shelves?" Cudless admits, "I'm not the most fashionable person." Yet he goes on to discuss the ways in which fashion inspires aspects of his projects and practice. Andrew clearly works across many disciplines, picking up on nuances in fabrication and form making that are repurposed and folded into his work. A great example of this is evident in a retelling of his account of the work he featured in 2016 at Design Miami, where he had created an installation for champagne maker Perrier Jouet. An extensive collection consisting of digitally fabricated oak veneer screens, a 3D printed cocktail table, and concrete benches. He also designed an ice bucket, which was fashioned out of Chardonnay grape skins by grinding the skins into a powder and then using that material to 3D print with. With that, please help me welcome Andrew Cudless.
Hi, everyone. I think I'm unmuted now. Thank you, Jeff, for that great introduction. I'm really excited to be here, and I've talked to the college community a couple of times since my interview almost a year and a half ago, and then at the beginning of the year to the freshmen. So I'm really excited to have an opportunity to speak to the whole college community, including alumni and all of the professionals watching tonight. I also wanted to thank the programs committee for the invitation. I'm really excited to be here, even virtually. Okay, so like Jeff said, the lecture is divided into 4 parts that have emerged in my practice over the last 15 years. For each of these topics, I'll attempt to trace a disciplinary concern through the development of my teaching and professional practice to the current day. As such, I'll try to show you how these ideas have evolved over time, often due to conversations with students and my academic and professional colleagues. So the first chapter deals with drawing in the age of automation. I never would have thought that or predicted that I had really anything to say about drawing. Because 25 years ago, when I was completing my first degree in architecture, it was actually my lack of drawing skills that pushed me towards computation. Compared to my peers, I was horrible at drafting, and I saw digital drafting and modeling as kind of a crutch that could help me keep up with my peers. Since then, the role of drawing, especially in the profession, has radically shifted and will continue to shift towards a model-based paradigm. So the relationship between drawing and architecture is foundational yet paradoxical. As Robin Evans suggests, architecture could be defined by the struggle between the inherently 2-dimensional plane of the drawing and the 3-dimensional reality of space. Architects must fold the complexities of construction, materiality, perspectival view into flat drawings, while at the same time unfolding the abstract rationality of the drawing back into built form. So for hundreds of years, architects have primarily conducted their work in the parallel space of projective drawings, plans, sections, axonometrics, and so on. With the advent of CAD software in the last few decades of the 20th century, the fundamental act of drawing was relatively unchanged, despite the new and different toolset. Only as digital modeling, and more recently, building information modeling, have become the dominant methods used to design architecture, has architects' relationship with drawing radically changed. After centuries of drawing being the essential mechanism to generate and critically engage architecture, we're at a moment where drawings might exist only as an output of production, if even that. Within a model-based design paradigm, the construction of drawings has either been bypassed altogether or been uncritically outsourced to algorithms. Drawings could be viewed as an anachronistic byproduct of the current legal requirements for building permits. In this void, what is the agency of drawing within the discipline? Or in other words, why do we draw? Freed from the complex historical interrelationship between drawing and building described by Evans, should we simply create buildings without drawings, as many have suggested? Or might the very technologies that have enabled this freedom be re-examined for their potential to critically engage drawing as a generative and creative act? So before we get into re-engaging computation or re-engaging drawing in relation to computation and automation, I think it's necessary to kind of back up and focus on kind of the pedagogies of computational design and their relationship or lack thereof with drawing. It's precisely the frustration that I have with these pedagogies that have led to several projects, which I'll show a little bit later. So on the slide, you see four basically categories or ways that I think computational design tools are taught in universities today. So for the first one in the upper left, design to production. So this is a really common, way of teaching many tools where they're taught through kind of a workflow that goes from the digital model to either robotic control or other types of productions, where essentially the drawing is seen as redundant and antithetical to the process. That if any drawing is needed, it's really just as an input for another machine for a toolpath or something like that. In the upper right, simulation and optimization. In this case, computational tools are taught in order to either simulate or optimize a particular process related to structural, energy, or other analysis topics. So in this case, drawings are simply a static representation of a dynamic process. Then we have building information modeling. In this case, and Jeff might be familiar from this from his time at Gary, that computational tools are taught as part of a philosophy that I refer to as one model to rule them all, whereby all drawings and data are generated through a central model-based platform. Here, the drawing is an afterthought required by the legal permitting process or processes. And then finally, in the lower right, we have case studies in parametricism. So in this case, computational tools are taught in universities in relation to the stylistic tropes that have unfortunately become synonymous with the tools. Many students don't know the difference between computational design and parametricism. Here, drawings, if used at all, are again, similar to the simulation technique, simply representations of a more idealized dynamic model. So furthermore, looking towards or forward into the profession, the need for drawing is rapidly being subsumed by new technologies. To give just a few examples, TestFit.io is developing a model-based tools that make early feasibility studies parametric. In a recent conversation with TestFit's CEO, Clifton Harness, he said their goal was to automate 80% of the tasks that architects currently perform through laborious drawing. Upcodes is developing software that could one day eliminate drawing-based permitting sets through real-time and automated model-based code checks. Their goal is to fast-track the permitting process by bypassing both physical and digital drawings as the primary evaluation media. So essentially, like imagine a button in Revit that you push and your model is analyzed for if it's compliant with the local building codes. And if it's not, it shows you where it's not and gives you hints on how to make your building compliant. And that if once it reaches compliance, that the building could be permitted. In the lower left, Fologram is developing augmented reality-based tools that could one day eliminate a contractor's need for drawings. Rather than contractors referring to either digital or physical drawings, they would be able to virtually see the building's model on site. And then finally in the lower right, the game engine-based rendering platforms like Lumion or Twinmotion or eventually things like Unreal, through their speed and realism have become the go-to tools for communicating with clients over the far more abstract drawings that architects are familiar with. So why draw? And how might drawing be productive in the age of automation? Kelly Baer, one of the contributors to the first volume of the Drawing Code Show, which I co-curated in 2017, has discussed how drawing, rigorously and intensely pursued, maintains a sense of surprise and innovative discovery. Quote, the drawing becomes a catapult for invention, leaving behind the expectations of convention, buildability, or financial burdens. The drawing is a proto-document of something that is not quite finished, an act still underway in the eye of the author. In this respect, drawing might capture the abstract logic of an idea better than another form of media. About 9 years ago, I changed my teaching methods for computational design from one based on famous case studies in contemporary architecture to one based on case studies from mid-century art and computation. This was based on a conversation I had with a student who, when I suggested he should use Grasshopper to complete his project, told me, "Oh, I never learned Grasshopper because I don't like twisting towers." And as the coordinator of design media, I knew that the student had taken a course in Grasshopper, but they had kind of willfully decided not to learn it because they thought it was only used for twisting towers. At that moment, I realized that my computational design pedagogy had failed to convey the rich capabilities of the tool, and many students simply thought these tools were only important if one was interested in parametricism as a style. For me, it would be like saying, I don't use keyboards because I don't write novels. There's a critical difference between the inherent value of a tool and how one particular group has used the tool. Using minimalist and abstract art as case studies allowed me to introduce and discuss the essential math, logic, and geometry topics to students without having to wade through how some of these techniques have been applied during the period that the architectural historian and theorist Mario Carpo has referred to as the first digital turn. In my own professional work, I've also explored the generative capacity of computational drawing to explore ideas. I think of these as computational sketches. If hand sketches could be called a direct connection between the mind and hand, computational sketches are a direct connection between mind and machine. These are thought experiments that are played out with computation as a partner, and for me, they often are seeds for future projects. In this particular computational sketch, the script starts from a simple seed geometry, in this case, a circle, but it could have been any shape. And at each generation, there's a random mutation that pushes or pulls the curve in or out. Each successive generation must then grow off of this new foundation. Small changes in the rate of mutation, its strength or variability, and the rate of growth produce large differences over time. I return to these computational sketches again and again in the way a craftsperson might return to her toolbox. I tune the script to produce new design opportunities or to align with material or fabrication parameters. I've used this particular computational sketch over the last 3 years to make robotically drawn ink drawings, ceramic 3D printed vessels, concrete benches for a forest cemetery, and a proposal for a rug for Louis Vuitton. In the same way an architect might return to a partie diagram repeatedly to mine new opportunities, I try to mine the generative capacity of algorithms. For an exhibition on computational drawing, I co-curated with Adam Marcus in the tense period between the 2016 election and Trump's inauguration. I wanted to explore how to use computation to help generate and represent a counterfactual walled city. Trump's constant ranting about the wall was chilling, disturbing, and reminded me of a medieval warlord. Obviously, the wall is an architectural device traditionally used to divide people and territory. Trump's talk of the wall reminded me of these maps of walled cities. I began to wonder if I could script a wall to somehow become simultaneously territory and city. What would a city look like if it was a wall and nothing else? I've been fascinated with walls that have kind of grown thick enough to become kind of buildings in and of themselves. So I started a computational sketch that slowly increases a wall's length while preventing it from moving outside a site or intersecting itself. At a certain point in the growth process, the wall takes over the entire site. There's still an inside and an outside to the wall, but sometimes the outside is deep inside the site boundary or vice versa. At that point, I was left with a big squiggly wall, but realized I needed some sort of roofscape to make it read as a city and not just a thickened line. I also wanted to push myself to learn new tools and wondered how far I could go in the automating of the representation of city life. As a thought experiment, the goal was to produce a sketch that was believable enough, with the help of automation, to spur questions about the nature of walls and their possible use to confuse sidedness and unite rather than divide a community. That's when I turned to Google's autocomplete feature to give me suggestions on what programs a rooftop might support. I worked my way from A to Z, pretty much accepting whatever suggestion Google's autocomplete gave me, and started designing parametric definitions that could implement that program on a number of different random sites along the wall. So essentially, I would just type in the word rooftop and then the letter A, And if it would give me 5 or 6 suggestions, and whatever suggestions seemed the most architectural to me, I would then design a script to produce an infinite number of those along the wall. So last year, my co-curator, Adam Marcus, and I had the opportunity to experiment with these ideas further with students during a one-day workshop at the University of Miami. Using a pre-built script, kind of a variation of the script that I had used in my own drawing, students that we provided to the students, we asked students to develop a seed algorithm that would produce a basic block pattern. Buildings, trees, crowds would then populate the city automatically. Students would then iterate with how the changes in the base seed pattern would result in massive changes in the whole urban pattern. Finally, we asked the students to almost work backwards, like archaeologists, to hypothesize on what political, cultural, geological, or economic systems might have led to their generated cities. The goal was not to become urban planners. Instead, it was to understand the biases embedded within the base geometry of our imagined cities. All right. So that's the first of the 4 chapters. The next chapter of the lecture is on the material practice of architecture. So after I finished my first architectural degree, I was lucky enough to have a fellowship, and I lived in Kyoto, Japan for a year. So like maybe some of you, especially those of you towards the end of your time at the college, after 5 years of being an architectural student, I wondered if architecture was actually for me. I decided to actually pursue a degree in traditional Japanese carpentry and had set out to spend the rest of my career in Japan. Although I didn't follow that path and I had to return home to the US, I learned that during the traditional training of a carpenter in Japan, the first year was focused solely on learning how to make your own tools. The idea was that until you mastered your own tools and materials, there was no point in working on buildings. So this idea of learning the tools and materials of your discipline before engaging in the production of the discipline stayed with me. I became fascinated with a diverse group of architects who seemed to have focused deeply on specific material systems, such as Dieste with bricks, Otto with fabric, Kendall with concrete, and Prouvé with sheet metal. Some of these practitioners embodied the historical archetype of the master builder in that they were not only the designers of the structures, but also the general contractors. At the same time, in my teaching, I'd become frustrated with the methods I was using to teach design. I was simply repeating the ways I was taught, and I had been focusing on site and program as the sole generators of design concepts. We're all familiar with the studio model of faculty introducing a site and program during the first week, followed by weeks of site and program analysis. The resulting projects of my students were good, but they also felt divorced from the material realities of construction and the possibilities available when one starts from a specific material system as the design generator. Basically, to kind of rephrase that in a different way, I feel that most architects actually have like, I'm not sure what to call them, fascinations, obsessions, biases of particular ways of making and designing. And they then tune those in order to apply them to different sites and different programs. Yet within the education of an architect, we often focus so much on site and program being kind of the drivers of not focusing on how to develop a personal and unique way of thinking about making. And if you look at, almost any famous architect, a lot of them are kind of like redoing the same design over and over again, using different, they're retuning their material practice in relation to different programs and sites, of course, but I think that material practice is at the heart of it. Like for Mies with steel and grids, I mean, I could go on and on, but it's something I think we don't focus enough on, and how to develop your own kind of thinking about the material practice. So in 2014, the frustration was too much, and I decided to flip my studio teaching around such that I would ask students to choose one material or one way of making and to produce 5 large egg-shaped objects over the first 4 weeks of the term. Only after they had blundered through the first couple of attempts would they begin to understand the craftsmanship required to work with the material and gain fluency with it. At that point, I would then introduce the program and site, and then they, with their new material knowledge, would begin to apply their material system to the design problem. In 2015, I was asked to rethink the MArch Studio 1 curriculum at CCA. Over the last 5 years, I've loved teaching the studio as it basically attempts to introduce students to new architecture, introduce students new to architecture to its material practice through hands-on experimentation. The term was divided into 7 two-week assignments that explored the relationship between material, form, and performance through full-scale assemblages and large drawings that together built what we referred to as totems. I wanted students to discover design opportunities that only come out of a deeper understanding of working with their hands, with concrete, wood, steel, and plastic or paper sheets. I wanted students to gain a deep respect for the labor of architecture and the laborers who make it possible. In fact, students told me afterwards, sometimes after they graduated, that they formed the kind of the close relationships that they had with their peers in the studio through, trying to figure out how to cast concrete at 10 p.m. in the rain or something like that. And then just the kind of need to ask for help and to lift something and to kind of laugh about how kind of crazy what they were doing was kind of the basis of a lot of friendships. So in 2018 and 19, I also introduced an 8th topic to the studio, which exists as a kind of meta project throughout the entire term. So 3 years ago, while finishing up Confluence Park with my colleague Tina Florian at Lake Flato, I asked her what was one thing she wished all architectural graduates knew when she hired them. I was expecting some sort of answer around a technical skill, but instead she said she wished architectural education better prepared architects for collaborative design. Very few projects in the profession are completed in isolation. Most require interpersonal skills that allow architects to quickly jump on or off projects and to build towards a collective goal. As such, over the past 2 years in the MArch Studio 1, I've had students switch projects every 2 weeks while building the totem. Despite having a lot of concerns that this would be a disaster, I was happily surprised how the projects were as good, if not better, than previous years as students working solo. Rather than each student being solely responsible for an entire project, they are essential collaborators of 7 different projects and can take collective pride and ownership in producing a much larger whole. So the way I sold this to students was I said, look, at the end of the term, you'll have 7 times as many projects to show in your portfolio. And you're not responsible for the entire thing, but you're responsible for 1/7 of each of these projects. And that's important. You had a hand in all of these. And you had to deal with, how do you hand a project off to someone who hasn't worked on it before? Or how do you jump onto a project that you don't know anything about? And in the profession, this type of thing happens all the time. And I was really kind of inspired by my friend Tina's comment about that, it being kind of maybe one of the most important attributes that an architect could learn. So moving to my own practice, I'll just mention 2 completed projects influenced by my desire to put material practice at the forefront of the design process. In 2015, I was commissioned by the champagne company Perrier-Jouet to produce an installation for their booth at Design Miami. Perrier-Jouet is one of the oldest champagne houses, and their founders amassed the largest private collection of Art Nouveau works in France. In fact, their own bottle was designed in 1902 by the glass artist Émile Gallet. I was asked by the company to reflect on their collection and to produce a new work inspired from it. 2 of the most prominent features of the art and design movement were its commitment to breaking down the distinctions between the fine and applied arts, and to its use of sinuous curves drawn from nature. These fibrous strands, often represented by vines or hair or flowers, unify a work by drawing your eye across it. I wanted to work with a series of different strands to produce the installation, but it wasn't until I visited their vineyards, the winery and caves in France, and the site in Design Miami that I began to form a material and spatial concept. My goal was to evoke the materials and processes used within the growing, processing, and storage of the champagne within the space at Design Miami. 4 materials were chosen from their site and process, and then developed into specific furniture or design objects within the space using a fibrous or strand geometry. Each of the 4 projects attempt to capture the organic, flowing geometry of the Art Nouveau period while using contemporary tools and fabrication techniques. So I'll step through each of these 4 quickly. For the 3 large oak screens that create a private experience away from the chaos of the exhibition hall, I explored how thin micro-veneers of oak could be cut and assembled into glowing fibrous strands. The parts are assembled without any glue and only require the interlocking of tabs to create a strong column. Each of the screens was composed of roughly 75 columns that create a clearing in a forest where visitors could rest, grab a glass of champagne in the relative peace and quiet before returning to the kind of chaos of the design fair, which if you haven't been, I'm kind of making it sound bad, but you should definitely go. It's not a bad thing at all. Design Miami's is incredibly inspiring, but it's like, imagine like going to IKEA, but instead of like cheap furniture, it's some of the most, it is the most finely crafted and designed furniture in the world. Many of which you'll seen in architectural history classes or design classes and so forth. But it's just, as a designer, I felt it was completely overwhelming to be in a space where there are thousands of people and all of these amazing pieces of design. And I needed kind of like I said, a clearing in the forest, like a place you could just go away from all of that energy. So the irony of Design Miami is that there are hundreds of chairs, but nowhere to sit. Each of the booths exhibits some of the most iconic chairs of the last century, but no one is allowed to sit on them. For the Perrier-Jouet booth, I wanted to create an oasis where visitors were free to relax. Using the hand-carved chalk caves of the winery as inspiration, I worked with Concrete Works in Oakland, California, to create a series of 16 concrete stools that mimicked the natural beauty of the caves. Each stool was identical, but through the use of an irregular hexagonal tiling, they can be moved into larger benches. It was great seeing visitors come into the space and actually be shocked that they could sit down. They would like look at me and they're like, really, I can sit? And it was kind of hilarious that they had to even ask. For the central table, I worked with my friends Ron Rael and Virginia Sanfratello at Emerging Objects in Oakland to print 7 large flutes that aggregated into a luminescent cocktail table. After being resistant to 3D printing for years, as I was turned off by the black box nature of the fabrication process, I learned how to program the G-code that runs the machines directly, which allowed me to create a woven pattern of the bioplastic strands that reference the wicker baskets used during harvest time. As the melting strands slump from one level to the next, they create a series of truss-like structures that greatly increase the stiffness of each leg. So you can kind of barely maybe see, but there are these kind of diagonal lines moving across the table. And that's really just the kind of slumping hot plastic draping from one level to the next and forming kind of like a diagonal truss running up and around each of the flutes. Finally, I wanted the ice bucket to be the most closely tied object to the actual champagne making process. If you think of champagne as the liquid essence of the grape, I wanted the ice bucket to represent the solid essence of the fruit. I wondered what happened to all of the skins and seeds after the juice was squeezed from the grape, and I set out to get some of this material, as it is usually discarded or composted in the winemaking process. Luckily, I found a startup in Sonoma that was actually collecting this material, the skins and seeds, and actually separating them, drying them, and then grinding them down into a gluten-free baking flour that they had just started selling at Whole Foods in San Francisco. So essentially you could actually go into a grocery store and buy, as you can see in the image in the upper right, you could buy like Chardonnay grape skins or Pinot Noir seeds or whatever, and the bread that you bake from it would actually kind of have the flavor of the different varieties of grapes. So I acquired a few buckets worth of the Chardonnay grape skin flour, and again, working with Emerging Objects, was able to 3D print the ice bucket components. Due to the limited size of the printer, we printed 8 interlocking parts that were then sealed to make them waterproof and then assembled into the final ice bucket. The rippled surface pattern of the bucket recalls the dried skins of the grape, like the surface of a raisin. The other project that I'll briefly mention in this chapter are the shelves I designed for Louis Vuitton's Object Nomad collection last year. My goal was to use the expressive potential of materials and fabrication processes to evoke my feelings on travel, which was the focus of the collection and what I was asked to kind of comment on. For me, I feel pulled in 2 directions whenever I travel. There is the tension between the lure of the unknown and the pull of the familiar, an inherent conflict between the joy of the new and the comfort of home. The shelf uses the strength of wood and the suppleness of leather to form a joint between 2 materials that evokes this tension and equilibrium of being pulled in 2 directions. For the freestanding version of the shelf, so I was, after designing the first version, I was asked to design a freestanding version. So first the hanging and then the freestanding. So I wanted to take this tension even further through producing material strangeness. I'm not really actually sure what to call it yet, but a material strangeness sounds good. The shelves appear to hang in space like the other version, but as your eye moves up, there's no apparent support. Through the use of 3D printing, you're able to produce slender aluminum branch columns that are embedded within the leather and are connected to the oak sleeves through hidden joints made with a 5-axis router. So this was really, I think, interesting experience for me, where I was completely stumped when Louis Vuitton came back to me and said, "We love the shelf, you know, the shelf that you designed. But not everyone has walls or ceilings that you could hang something from. So could you make this, but it just has to stand up on its own?" And I had no idea for a couple of weeks how to do it. And I actually originally proposed like almost like a swing set type structure, like columns on either side and a beam running along the top, and then hanging the shelves like a swing in between. And they came back to me and they said, no, you misunderstand. Like, we want like exactly what you have, but it can't be hanging. And so I struggled with that for a long time. Like, how do you make something, you know, because of my tendency of like wanting to be kind of like true to the physical forces within the project, to like fake that it was hanging, it felt like really strange to me. So I decided at first to actually reverse the direction of all of the kind of bumps on the wood, so that it actually appeared as if the structure was in compression. And after looking at it, it actually just looked even worse in a way, because the columns have this inherent tension to them. And in the end, it just seemed actually a lot more interesting to kind of produce this thing that appears like it almost like a trick of the eye, where you think it's hanging and you could be looking at it for a minute or two and not realize that it's just sitting on the ground and completely stable. So the 3rd chapter of the lecture is named after the subtitle of Tim Morton's book, A Professor at Rice. And the book's title, Humankind, Solidarity with Non-Human People. I'm using it as it best describes a number of trajectories and desires within my teaching and practice. I began my architectural education in the early 1990s at the transition between the postmodernist and deconstructionist trends within architecture. Neither movement, I feel, held much influence on my education, as they both felt divorced from the real or the natural world. And I felt more like clever games accessible to a select few. Instead, probably the most influential book from that time was On Weathering from Mohsen Mostafavi and David Leatherbarrow, exploring the ways in which water, lichen, and other organisms and processes change architecture over time. And maybe more critically, the ways that architects have or have not kind of worked with those processes. Similarly, there have been other books like 1,000 Years of Nonlinear History, Subnature by David Gisson, Animals as Neighbors, that have influenced me over the last 20 years. I was lucky enough to share an office with David Gisson as he was writing Subnature. Its focus on the often forgotten life outside of LEED certified world of corporate architecture's engagement with nature was enlightening to me. Similarly, Delanda's evocation of the organization and evolution of biological, geological, and cultural entities, and O'Connor's unveiling of the non-human life that surrounds us and pervades our cities and buildings, have expanded my understanding of my own role as a designer and an inhabitant of the world. Urbanization and industrialization have increased the physical and conceptual distances between humans and non-humans. Our cities and landscapes have created a sort of toxic monoculture of humanity. Furthermore, the way in which contemporary architecture engages the non-human world could be generally categorized into total rejection or the non-human as pest, which you can see, I think, best exemplified by the photograph in the upper left of a tree in London that the wealthy people living in the neighborhood were upset that birds kept on pooping on their cars. So they started putting pigeon spikes on trees so that birds couldn't land in trees any longer. So to go back to the list here, the ways in which contemporary architecture engages the non-human world could be categorized into total rejection or animals as pests, reduction, the middle photograph, of sustainability's focus on energy as kind of the primary source of re-engaging the world, let's say, or benevolent separation, in other words, the picturesque, which, you know, nothing against these projects. It's just more of a, these were two classic examples of the picturesque within architecture. Basically, the relationship between architecture and nature is one of separation, and that nature is over there, architecture is over here, and that's the end of the story. In my teaching over the last few years, I've attempted to discover or rediscover other ways of living with the non-human. In 2018, I co-taught an advanced studio with Nathan Lynch, the chair of ceramics at CCA, and we used this image of the 1886 Sylvester rotting sod house in Nebraska as a studio prompt. The photograph is primarily a portrait of a rural human family and their earthen home. Yet it also captures multiple non-human species that were essential for the human family's survival. Some of these species are wild, some domestic, and some in the kind of symbiotic, commensal, parasitic limbo in between. Yet they form a web of connections that envelop the architecture of the home. In fact, also the architecture of the body, let's say. In an age when we are finally recognizing the extent of our deep relationships with the environment around us and the microbiome within us, this studio sought a form of solidarity with the non-human. So Donna Haraway, paraphrasing Bruno Latour, states, quote, "We have never been human," end quote. When 90% of the cells of our bodies are non-human, it's impossible to build a wall between us and them. We co-evolve, constantly adjusting to each other and forming symbiotic or commensal and sometimes parasitic relationships that are often incredibly complex to unravel. So our student Maya Anoti's wonderful project, she explored the ecology of a specific bat species endemic to the agave plantations of Mexico and developed a ceramic wall system that would increase the habitat opportunities for the bats, the primary pollinator of the agave plant. The bricks were designed to be hollow to allow pregnant and nursing bats the necessary warmer microclimate, while the male and other female bats occupied the cooler exterior folds of the brick. In Nick Tanji's project, he responded to the predation of a particular native species of gecko, which is also the primary pollinator on his home island of Mauritius, by an invasive and larger species of gecko, by producing a column system that would allow for the native species to move and nest within it. So this term, I'm currently teaching a studio at Hines College that continues to explore these ideas with species native to the Houston region. The idea is to expand our understanding of who we design for, to include the life that surrounds us. We are living in their environment as much as they live in ours. So in my own work, my early exploration of the non-human life primarily focused on biomimetic formal and structural systems that were inspired by natural growth patterns. Later on, I began to explore ways of fabricating components that use self-organizing systems to discover stable states. The P-Wall series of projects was originally developed as a living facade system. However, when one version was commissioned for SF MoMA, it became an art piece hanging statically in a museum. In response, I produced this alternative fictional version to help me envision my understanding of the project in its intended environment. I wanted moss and lichen to grow on it. I wanted birds and insects to call it home. Although sometimes interpreted as an abstract melting of the white gallery walls, I wanted it to be much more alive and inviting to the life around it. There is a resonance that the wall has with our own bodies. People are drawn to it. It looks soft, but is rock hard. And despite that, people want to feel and hug it. The wall and our bodies share geometries because we share a similar material process. The human body is essentially a liquid interior held back by an elastic skin and held up by a compressive skeleton. The forms that emerged in the wall were a result of a similar interaction between the rigid frame, the elastic fabric, and the liquid slurry of plaster. As a designer, one of the things I learned from this series of projects was to give up control to these other forces. That is, I was a better designer when I partnered with other life and forces in the design process. I could create things that were beyond my own ability to draw or model them. We need to rethink the way that architecture has created an artificial division between humans and the richness of the world. We need to develop strategies that move beyond sustainability or the picturesque and actually invite the living and non-living world into architecture as both a design partner and neighbor. Finally, the last chapter of the lecture will focus on the integration of form, fabrication, and performance. Building on the last chapter, I see natural forms, forms built through geological or non-human agency, as a starting point to finding a better integration between the geometry of a building, the way it is made, and the way it performs. Excuse me. If we are going to discuss the forms we find in nature, we need to talk about how these forms come into being. As architects, we are used to talking about form, but we often do so in a way that separates form from matter. About 100 years ago, the zoologist Darcy Thompson was also struggling with this disassociation in his own discipline between form and matter. At the time, a battle was raging between the Darwinists, who believed form was simply the result of natural selection, and the vitalists, who believed natural form simply appear through a mysterious vital energy. Thompson's contribution to this was to reveal how the physical forces, such as gravity, surface tension, and many others, led to formal patterns we see across both the organic and inorganic worlds. And obviously I'm using the title of his book as the title of this chapter and the title of the lecture. So to quote Darcy Thompson, the form then of any portion of matter, whether it be living or dead, and I should mention here, when he says the word dead, he doesn't mean dead living matter or matter that used to be alive. He means matter that is like inorganic or like a mountain or the wind or something like that. And the changes of form, which are apparent in its movements and in its growth, may in all cases alike be described as due to the action of force. In short, the form of an object is a diagram of forces. I was immediately drawn to this way of thinking and how it has influenced a range of architects and engineers, such as Gaudi, Otto, and Eisler. Form isn't something abstract, but a mediator of force and the result of a specific material logic. Over the last 12 years, I began experimenting with ways in which fabrication data and structural performance could be integrated into the design process, rather than something that was simply addressed at the end of the design process. In 2012, I taught a 4-day workshop at the University of Minnesota, where students developed a small pavilion made from $200 worth of cardboard. The amazing thing about this structure was that I was sure that was going to fail. Only as the last few cardboard components were added to complete the structural flow through the thin surface did it become rigid. Later that year, I collaborated with Riyad Juka in Hong Kong on the Shellstar Pavilion. The project was designed and fabricated over 6 weeks and was only possible through the tight integration of form, fabrication, and performance data within the model. This trajectory in my work led to Confluence Park. Started in 2014 through the opening in 2018. I'll spend the rest of the talk, maybe another 10 minutes or less, on discussing this design and fabrication for the project. I want to begin by recognizing my partners on this project. I mentioned Tina Florian previously, who was actually one of my kind of flatmates in college and undergrad, and is now a partner at Lake Flato, and was the project manager for the project. Chuck Neves was the project engineer at Architectural Engineers Collaborative, and Josh Zabel was the project lead at Chrysler and Associates, the fabricator for the formwork. I'll focus on the design, engineering, and fabrication of this innovative tilt-up concrete structure using fiberglass composite molds. The design was produced through a small but multidisciplinary team that valued the integration of form, fabrication, and performance through the application of biomimetic principles, computational design and fabrication, and original construction logics. The Bhp Pavilion is in San Antonio, Texas, and is the central outdoor classroom and community hub of Confluence Park. There were three primary project objectives that the pavilion needed to satisfy. The first objective was to create an educational space that would integrate the architecture of the pavilion with the client's mission to educate the community on the critical role of water in the regional ecosystem. The second objective was to create a unique and inspiring iconic pavilion to help catalyze a new identity for this historically underappreciated part of the city. The final objective was to use innovative fabrication technologies and methods to lower the overall project costs while meeting the client's ambitious educational and aesthetic vision. While most structures attempt to visually minimize the shedding of rainwater, we decided to use the pavilion to celebrate the collection of rainwater and to make the form of the pavilion a pedagogical device for the park's guides and visiting teachers. The form that emerged from this process was based on the doubly curved fronds of many local plant species that cantilever out to collect and redirect dew and rainwater back to their root stem. The double curvature not only gives these cantilevers more strength, but the curvature also creates a channel on the top surface for the efficient flow of water. Rather than design a singular large shell pushing water towards the structure's fringes, we started to design several funnel-like doubly curved forms that opened up to the sky and channeled the rain into an underground cistern where it would be reused for the site's irrigation and toilets. Although the new doubly curved funnels aligned with the pedagogical mission of the client, the complexity of making these forms initially resisted easy construction strategies. Early designs for the funnels involved complex steel and cable net structures, which, even if each was identical, were beyond the modest project budgets. And I want to note here, so you can see the date, I put dates on this image and the next three images, so you can just see, as students, how fast sometimes projects completely take new directions. So this was December 4th, 14. So at this point, about a month later, inspired by the work of Felix Kendall, Heinz Eisler, and many others who had investigated the use of concrete to create complex forms that aligned with structural forces, the team quickly moved to concrete as the primary material. It became necessary to begin to divide the funnel shapes into discrete parts in order to break the forms into manageable sections, while also allowing views into the interior of the funnels. So if you think about each of these funnels, was essentially going to become a waterfall in a rainstorm. However, while the earlier steel funnel shapes were designed to cantilever and be supported through tension rings that could balance the forces around the entire funnel, the discrete concrete parts no longer had this tension ring and required a new solution. The design team decided on a simple solution of pairing each discrete funnel part with a symmetric paired element to create 11 structurally independent arches. So the resulting arch is the simplest of structures, the statically determinate three-hinge arch. An arch structure plays to concrete's significant compressive strength while minimizing its limited tensile strength. Referring back to the biomimetic inspiration, each of these metal. And just to be clear, I'll show it later, but each of these, they're fully structurally independent, that even the foundations, that if any of the arches settle in some way, they don't affect the arch next to them. An additional benefit to this new organization of petals or half arches was the idea of using a modified tilt-up concrete fabrication strategy. Tilt-up concrete construction, famously used at the Schindler House in 1921, is defined by concrete panels being cast flat on the ground on site and then lifted or tilted into place and connected to the foundation and adjacent panels. The technique can be considered halfway between cast in place concrete and precast concrete, as the panels are cast on site but not in place. Thomas Edison, who I was surprised to learn was one of the early originators of the technique, stated that the advantage of tilt-up is that it, quote, eliminates the costly, cumbersome practice of erecting 2 wooden walls to get 1 concrete one. In the context of Confluence Park, tilt-up had a distinct advantage over cast-in-place concrete, as it more easily allowed for reusable molds, which could be erected in one place on site throughout the construction phase. When working with modular systems, it's difficult to escape organizing systems that reinforce the appearance of repetition. After exploring various uniform grids, an irregular pentagonal tiling grid was developed. Sorry. The chiropentagonal tile has 4 long edges of the same length and 1 short side. When this pentagon is subdivided into 5 triangles, it results in only 3 unique triangles, 2 A's, 2 B's, and 1 C, which is probably very small on your screen, but just, let's see which, nope, that direction right there. You can see, or actually further over there. In the second drawing from the left, you can see the organization of the A, B, and C tiles. The center of each pentagon represents a funnel drain, and the edges of the pentagon represent the apex of each arch. Each A triangle is paired with its mirror B triangle from an adjacent pentagon to produce a full arch. Similarly, each C triangle is paired with another C triangle from an adjacent pentagon to form an arch. In order to produce the final pavilion plan, various selections of A, B, and CC arches were explored and analyzed for the shade produced, as well as the informality of the arches when seen in perspective. The design team tried multiple options of arch arrangements to produce a pattern that was both completely modular, yet appeared irregular. So just to kind of be more clear about that, is that early on, I'd actually used a regular triangular grid of equilateral triangles. I used a square grid and a hexagonal grid and things like that. But although it produced tiles that were all uniform and modular, from the point of view of the visitor, all of the columns would always line up. Whenever you looked at them, they would always form a line. And I wanted the location of those columns to be less formal. And it was that constant struggle between how do you have the appearance of something that is irregular while still taking advantage of the regularity of the modular system. So in parallel with the selection of the specific plan arrangements, development of the sectional properties of the geometry were also being developed. For both structural reasons and water flow capture, the petals had to retain double curvature. In order to test how water would flow on the petals, a rainwater simulation script was developed. So basically, all of these blue lines that you see are raindrops kind of running down the surface of the top surface of the concrete. And I would simulate that how rain would move on the surface. And if I saw locations where the rain wasn't flowing down towards the cistern, I would then modify the parameters of the petal to produce the channel that was needed. Although a traditional wooden formwork technique was explored, similar to how Felix Kendall made many of his structures, it was determined to be far too expensive and inaccurate for the project. Instead, we worked with Chrysler & Associates to develop a fiberglass composite mold. So basically, this was the way the contractor wanted to do the project of building a giant plywood and 2x4 structure underneath of the entire project. And the cost for all of the formwork came back, the bid for it. Well, first we could hardly get any bids. And then the bids that did come back were more than the entire project budget. So, you know, that all of this wood would just be thrown away. And it just seemed crazy to spend the majority of the budget, or more than the budget, which obviously we couldn't have, on simply waste material in the construction process. Historically, digital fabrication has been used in some of the largest and most expensive projects, while less expensive projects use traditional techniques. However, in this case, the traditional technique was far more expensive than the digitally fabricated fiberglass mold. In addition, the fiberglass mold was not only less expensive, but it was stronger, more durable, and more accurate. The 3 formwork modules were fabricated off of 5-axis and 7-axis CNC or robotically milled EPS foam forms. After milling the forms, a 50mm thick composite structure composed of inner and outer layers of fiberglass composite with a central core of balsa wood was applied. So you can see in the image behind my head that basically there's like maybe 1/8 of an inch or maybe a little bit thicker layer of fiberglass, and then 2 inches of balsa wood. That's what's called calendared balsa wood. So they take blocks of balsa and glue them to a piece of canvas, basically. And that allows you to kind of stretch, to bend blocks of wood in 2 directions on the surface. And because there's small kind of cracks between each piece of wood, so the blocks can kind of twist this way or twist that way. And in the end, the resin fills in the gaps between the blocks and essentially acts as like the webbing of a truss between the top and bottom chords. So you end up with an incredibly lightweight but strong 2-dimensional structure or 3-dimensional structure. One of the biggest advantages of using this method was that the milled surface of the foam positive was highly accurate and that all accumulation errors inherent to any fabrication process were offset from this surface instead of working towards it, as would have been the case if we had used a traditional method like what Kendall used in many of his projects, where they build up a kind of subframe similar to what you see behind my head of 2x4s, lay down plywood in one direction, lay it down in the other direction, and keep on laying it up until you reach the final shape. That in all of that, there's so much accumulation error that it was kind of outside of the realm of what we could really do with the project, that it wouldn't be accurate enough to kind of reproduce that over and over again 10 times for the number of molds or number of casts that we needed. Due to the size of each full petal formwork, roughly about 30 feet wide and 28 feet tall, each of the modules had to be subdivided into 3 primary subsections, in addition to several side forms that could be shipped to Texas. After the formwork was positioned such that it could be cast as a modified tilt-up wall construction, the rebar was added to the formwork. The fact that the bottom surface of each petal was cast against the smooth fiberglass, while the top surface was cast open to the air, allowed the 2 sides of the petal to have radically different finishes. In order to have the petals resonate with the flow of water, even when it was not raining, the open top surface of each petal was broom finished with the direction of the broom aligning with the flow direction of the water, which you'll see in a moment was really complicated because in order to have the pieces cast at the proper angle, so you can imagine like each of the pieces is going to eventually be half of an arch like that, but we couldn't cast it in that shape. We had to cast it 45-degree angle. So the downhill direction is now, the eventual downhill direction is not the direction here. So like teaching the laborers how to look at the shape that they're broom finishing and broom it in, to be able to like twist the project in their head so they could always tell which direction was down. Essentially repeating the kind of particle simulation I did with the rainflow analysis. So in the end, the 3 molds were used to cast a total of 28 concrete petals ranging from 20 to 36 metric tons each. Here you can see the construction workers broom finishing the top surface of one of the petals as it lays at its 45-degree casting angle. So you can see right behind my head now, the broom. They actually had to build a new type of broom that had they had to connect a 2x4 to a broom handle because in order to get to the very middle of the surface. Petals were cast in pairs and 2 cranes were used to lift each petal from its formwork to its final position. As you can see here, the petal is moved both in plan and rotated in section by the crane and then attached to the foundation and to its neighboring petal. So there's actually a hinge joint at the top, 2 hinge joints at the top of each petal that allow the structure, if there is any differential settling in the ground, that the whole entire structure can kind of rotate so that you don't get cracks in the concrete. Although the structure appears as a network of connected vaults similar to many shell structures, each arch is structurally independent. Not only did this reduce lateral loads being passed between arches, it also allowed for more easily fabricating the entire structure from only 3 unique molds, which reduced the construction waste. The project demonstrates that when a diverse and collaborative team focuses on the smart application of new technologies and focuses on the integration of form, fabrication, and performance, innovative projects that meet the client's mission are possible even within modest project budgets. All right, so that concludes my lecture. Thank you all for your patience and your time tonight, and I'd be happy to answer any questions that you might have.
Thank you so much, Andrew. That was fantastic. So we are going to take a few questions from audience members. And the first one is from an anonymous attendee. What techniques do you use in your ideation phase in order to stay open-minded to new ideas and not get boxed in with one thought?
That's a really good question. I think when I was a student, and I think I still suffer from this, that maybe, I'm not sure if it was because I liked like building models so much that I would, I often would like stop the design process much earlier than I should have, I think, because I would know that like to build a really good model, I'd have to spend a month building it, you know, or something like that. And it got me to this point where I would like work on the design, and then I would just say, okay, that's all I can do right now. There are a ton of problems, but I need to like move on and like focus on other things, on like other way of like communicating this design to other people. I can't just keep on iterating and iterating and iterating. So I still struggle with that because often I'll like come up with an idea. I'm like, all right, that's it. That's what we're doing. And then I'll go down the road, you know, for a few weeks. And it happened with Confluence Park that, you know, what you see behind me there, and you saw part of the design process. What I left out of that was the first 2 months where it actually looked like one big kind of dome structure, and all the water was kind of shedding to the exterior instead of coming into the structure. And I struggled with it because I was like, this is what we all talked about. The client liked it, I like it, but something just doesn't feel right. And I had to just basically come to terms with it and say, okay, I need to come up with something new, and I'm going to do it on my own, and then present it to the client and see what happens from there. And they liked it, and we went on from there and developed it. And I'm really glad that I'm getting better, I think, at not always latching on to the first thing or the first couple of things, and to kind of creating room in the process to like take the other path in the design. The other thing I mentioned, you know, in relation to the computational sketching that I find really helpful is that, you know, when I'm doing that type of sketching, like I might produce dozens or hundreds of different variations really, really quickly. And depending on how I've set up the parameters, they could be all very similar or they could be radically different. And I think that helps kind of get me sometimes out of the feeling that like what I'm working on right now is the fixed thing, that I can kind of continue to think through the parameters, and like in the same way you might like tune like, you know, a stereo system or something like that. Not that anyone has those anymore, but that you would like, you know, zero in on something and know that at the beginning it doesn't have to be perfect, and that the tool will help you craft that as you gain more information, more ideas around the project.
That's great. Thank you, Andrew. Next question comes from Abraham Tanvir. You described other architects who have specialized in a particular material. An example would be Kendall. With your designs expanding across material mediums, Have you found a material that would most align with your work, or do you tend to keep your options open?
That's a good question too. Yeah, I mean, although I identify with like Candela or Dieste or anything like that, I think I maybe identify more with like the meta version of that, of like not just one material system, but the idea of thinking through a material system is kind of what I identify with. And that I'm I don't know, maybe I'm constantly obsessed in like researching new materials and new ways of using old materials, and or just old ways of using old materials. And I don't feel like I'm tied to any particular material. I think each material has its own advantages and disadvantages. Like I love Confluence Park and the use of concrete in it, but I also know that concrete is, you know, from a energy standpoint, carbon standpoint, it's also not the best material. I've always loved working with wood, and I think it's probably my favorite, I guess. But even there, looking at like with the oak veneer screens I did for Design Miami, I was just interested in like other ways of working with oak other than the kind of solidity of it, of like how could you make oak feel light and glowing.
Great, thank you, Andrew. Our next question is from Marie Lege. Great work, thanks for the lecture. Did you add any special additives like Zyprex to the concrete in Confluence Park to keep the concrete watertight? What was the mixture?
That's a good question, but it's definitely, I don't know the specific recipe, and if I did, I don't know if I could even reveal it. I know that it was a huge process, and I'll tell you just a little bit about it. So, you know, one of the biggest problems was how do you get the concrete to be liquid enough that it would flow, you know, down into the kind of the column area of it, but not too liquidy that it could still stay like up on the 45-degree angle kind of flanges of it. Because there wasn't a lot of room to like be able to get a vibrator down into the column area. And it took actually a couple of tries, and actually the I don't know, maybe a secret of Confluence Park, maybe not a secret anymore, is that if you visit Confluence Park, there are 3 kind of satellite pavilions, which are actually just the C modules where we put a block in the mold and cut the bottom 10 feet of the column off, essentially, so that the concrete wouldn't flow into that part of the mold. So they're only 17 feet high instead of 27 feet high or whatever. And so the contractor wanted to start with those because they were the smallest ones. And if they got something wrong, they, you know, only got it wrong on the small ones instead of the big ones. So when I first showed up after the first panel was cast, they had cast one of these 17-foot high ones, and it was really disappointing at first, and the concrete was incredibly bad. Like you could even see the rebar sometimes, like the rebar wasn't covered. And they were like, is this good enough? And we're like, no. And they're like, that's going to be about $80,000 that we have to eat if, you know, we knock this down. And we're like, it's just not good enough from a structural standpoint. It won't, you know, water can't get into the rebar. And we had to, you know, luckily they got it right on the next few tries, and it got better and better throughout the entire process. But it is really like cooking, and it took a lot of prototypes. Some of them are still there, like the next set of arches, the second of the satellite prototypes or the satellite pavilions. They decided to, what's the term? Put a top coat over the entire structure because it was full of so many little holes, bug holes and things, and without asking us. And we were like, look, we're okay with some holes and some irregularity. It doesn't need to look like, you know, stucco. And so it kind of took a lot of trial and error on both, on all of our parts to kind of get the mix right. But yeah, on the specific recipe, I don't know it off the top of my head.
So we have 6 more questions. So we'll try to kind of go through these in order. Our first question is from Mehdi Farah. She's comments, fabulous presentation. It's a 2-part question. 1, how do you define robots in architecture? And 2, can robots be involved in the design process, or are they primarily fabrication tools?
That's a good question too. I mean, it really depends on how you define robot and how. So, I mean, I guess I would define robots as more physical rather than virtual things, and I think they will have an incredible impact on architecture in the coming years. The manufacturing process throughout the world went through an automation, switch to automation, that greatly increased, productivity and the ability to make, many things in the world that would have been incredibly difficult to make any other way. Architecture has never gone through that automation because the difficulties of working outside, the difficulty of the way that we design as architects, that everything is always a one-off custom project. Not always, but almost always it's a custom project. And one of the difficulties I've had is that even the way that the robots are designed, that they were designed for the manufacturing industry, for the automotive industry, for the electronics industry. So like my phone, by default, like my phone has way more memory and processing power than the average robot. That robots, the way that robots are designed is that they're designed to do like one thing over and over and over again. Like weld, one seam on a car or something like that. And it was only in the last like 10 or so years that has begun to shift, and that the way that you think about programming a robot has shifted away from the, we're going to hire a programmer to develop, this one algorithm that controls the robot to do one thing, and then the robot is going to sit there for 365 days a year, 24 hours a day, doing that same exact thing. It's really good for making cars, but it's not good for making architecture. And so I think there's been a shift within the robotics industry to make them much more flexible and adaptable to customization. But it's also a shift that I think we need to go through within architecture to think through how to, that maybe not everything has to be so highly customized, because in some ways I think we've like designed ourselves out of the profession in a way, that the vast majority of things are not designed by architects. And I think that if we thought through some of the concepts and related manufacturing and fabrication issues related to robots, that we could have a much greater impact on the built environment.
So I have just a quick comment from Sharon Lott. She says, I appreciate you sharing how these kinds of weaknesses, like not being particularly great at drawing, can set you up on a path towards developing an expertise that suits you as a designer. I just thought it was quite nice in relation to, the kind of opening dialogue you had with your lecture, Andrew, and maybe just wanted to, kind of comment on that.
Yeah, I mean, I think the profession is big enough for everyone, like there's, just because you might not be good at drawing or might not be good at modeling or whatever, you might be an amazing project manager. You might be, who knows? And I think too often within the education of an architect, we're trying to educate everyone to be the like celebrity architect. And as I said, kind of in the middle of the lecture, like even those projects don't happen in isolation. In the media, we tend to think like, oh, that's the whoever's project. But in reality, it was probably like, 3 or 4 recent graduates and like a project manager with 5 years experience, and maybe someone with 10, 15 years experience coming in every couple of weeks to check in, right? So I think there's the work happens incredibly collaboratively. And because of that, there's room for a lot of different people's talents. And so you should think, rather than thinking of like your weaknesses as like your downfall, it's just like, it's actually more of like helping you find opportunities that, that you can have an effect within your career.
Great, thank you, Andrew. Someone asked, how has your computational work informed your non-computational work?
That's a good question too. Trying to think of what my non-computational work is. I like, even when I'm doing like ceramics or something like that, that I'm often, I think, even if I'm not even using 3D printing or something like that, I'm often, and I think it's just my nature, I'm often just thinking algorithmically through the process. And I often tell my students that it's more important that they understand the generative logic of how their project comes together than actually being able to like code it or script it or whatever. And that, you know, a lot of those things are really hard, that they don't come naturally. Like, it's like learning a different language or something. Literally, sometimes it is learning a different language. And I think it's more important to have a good handle on what the logic is of a project. And in the end, it doesn't really matter if it's done computationally or if it's done in an analog way, because I think the power there is understanding the relationships between all of the concepts and materials and geometry and so forth.
Great, thanks, Andrew. This is actually a really wonderful question from a student. I'm personally learning coding while in architecture school, but they've taken issue kind of merging these two worlds, coding and architecture. How do you view merging different studies that seem kind of perhaps difficult to combine with design, like biology, chemistry, psychology? I think these are all things that you know, you're definitely incorporating or at least participating in.
Well, I mean, number one, definitely collaboration. You know, like, I'm interested in all of these things, but I'm also not like an expert in maybe any of them. And you know, I started out, I don't know, in 2003 learning how to code, and I never coded anything before. And then by 2006 or 7 or something like that, when there was something called generative components, and then the CATIA digital project, and then Grasshopper, eventually these kind of more visual programming ways came around. At first I kind of scoffed at them and I was like, oh, toys, whatever, like you can't do, you know, coding is the real way to do anything. And I realized pretty quickly how kind of ridiculous that was, and that I taught a scripting course with students, and I think there were 20 students in the course. And at the end of the course, I asked them, you know, how many people in the course think they'll use coding in their career? And 2 people raised their hand, and they actually have gone on and have, you know, one works at Autodesk and another I think works at Snowhetta. And they've gone off and done, you know, amazing things. But the other people in the class said, you know, another guy who ended up becoming one of the heads of design at Airbnb, said, I'm really happy I know this, but I never want to do it again. And and I think that was good. It was like, I think it was really helpful to like know, like I thought that was actually a success in a way, but it was also, it was like, well, maybe I need to find another way that students will have more access to this technology, rather than just seeing it as something that's good to know, but that they wouldn't use it. And that's when I kind of decided to just shift most of my teaching and even my professional work over to doing visual programming. And that, like, because I wasn't an expert, and I could do, if something to calculate instead of 5 seconds to calculate, it wasn't a big deal, you know, for me. Like, if this was something that I was rolling out to an entire company or something like that, I would definitely want to bring in a computer programmer to help, you know, do it the right way. So I think, I mean, I'm impressed that you're doing both, and I think you should, and there will be many opportunities, I think, for you in the coming years, because I think there are more and more ways that these two worlds are getting closer.
Okay, Joe, we're going to do two more questions. There's a few questions that I'm going to combine, which is kind of like a software recommendation. So there's been a few students who've mentioned that they're interested in computation design and algorithms and thinking about ways in which they can incorporate them into their work. From the standpoint of a student, what would your kind of starting point be, or what literature would you perhaps jump into first?
Mm-hmm. Well, I guess the first thing, I can make a plug for my class next term, Introduction to Computational Design. I don't remember the day of the week or the time. I think it's Wednesday mornings, maybe, I don't know. But also Jeff is going to be teaching an elective next term, and there'll be, I think, maybe 4 other design media electives that are all really, really good. And just look in your email. I'll be sending out a kind of like mini catalog of just the design media electives so that you know kind of what to look for as you sign up for classes. Okay, enough of the plug. The other part of the question would be like, well, number one, you should learn while doing. I think it's really, really hard if you just try to like follow some like a tutorial in the abstract. Like I've tried to learn a few different programming languages that like I'll go through all the tutorials and online videos online and buy books and things like that. And it like all of it goes out of my head almost immediately, unless I have a project to immediately apply it to. Because as soon as you have a project, you have like bugs that come up that aren't, part of the tutorial, like that you might look at in a book or something like that. And those bugs are good because they cause you to understand like the software, the process even better. You realize it's just like learning a language, that when you first start learning a language, like you kind of sound like you don't know what you're saying. You're not using the right verbs or nouns or grammar or whatever it might be. And that the more you talk to people in the language, the more you learn. And just learning through a textbook is I think really difficult for human spoken languages, but it's the same exact thing for learning software. That you should find something. It doesn't matter what it is. It could be a studio project. It could be redoing your old studio project. It could be building, I don't know, a nightstand in your bedroom. It doesn't really matter. That it's just something that you can immediately apply the ideas to. The other thing I'll mention is that specifically, I think one of the huge advantages of actually both text-based programming as well as visual programming is that there are so many resources where you can just download, the someone's project. And unlike like if I were to download like a Rhino model, I might not have any idea how that model was created. Like it's really hard to deconstruct a digital model. But if you download the code or the Grasshopper script or something like that, you can look at why or how someone built that. And then you can kind of reconstruct it again. And then you can decide actually the way that they built it maybe doesn't make sense for my project. I'm going to hack it and redo it my way. And I think that's the way that I've learned most things. I think it's the way that we learn most things in general, is to just look at how people are doing it and then imitate it and then change it to be how you want.
Yeah, lots of copy paste would be my my recommendation.
Why isn't it working?
Yeah, exactly, and then figure out why it's broken. So our last question, and I wonder, Andrew, if you maybe can answer this in relation to Timothy Morton, some of the aspects of dark ecology, thinking about pulling away from a pastoral or kind of romanticized idea of nature. Mm-hmm. The question is, do you have any interest in pursuing biomimicry and incorporating that into your projects?
Let's see. So, I mean, I mentioned biomimicry, I think a couple of times in the lecture, like with the petals, the concrete petals, kind of mimicking the fronds of plants. And I was trained at the AA in London with a biologist who his whole career, he was an engineer, but he was basically an engineer of nature in a way. So he studied the structure of trees, how a seed gets thrown from its case, like a pine cone or something like that, as the pine cone dries and it ejects the seed to, far out away from the tree that dropped it. So I think for my whole career, I've been thinking about biology and biomimetics. I think one of the things I've always struggled with, though, is, there's just all these different terms, the difference between biomimetics, biophilia, biomorphism, things like that, of like, are you imitating the shape of something? Are you simply, or are you imitating and like learning from the kind of the performance of something? Or in the case of biophilia, is it more of like a psychological, that somehow the natural form, and I'm not sure exactly how I feel on this topic, but there's theories of how certain forms psychologically affect people, like having or not just forms, but I mean, I guess you could say forms, like having a window in a hospital room will, the classic example from biophilia, that like having a view of nature will heal you sooner. So I'm not sure how I can tie all of that back together to Timothy Morton. But I would just say, I mean, I just really appreciate his work, and at least the work that I can understand of his, that I think, like I was saying, I think several times in the talk, of like thinking about like the us versus them aspect of I mean, the duality we often put together of like there's man, and then there's humans, and there's nature, or something like that, of the duality. And I think thinking through more the kind of solidarity with the rest of the world, and how I said that like we are in, like a wasp's environment as much as they're in our environment. And I've just been fascinated with the kind of negotiations that occur between species, be it, companion species like dogs and cats and something like that with humans, or these other species that we don't even know they exist in our day-to-day existence, but we're completely dependent on them, like the species that live inside of us. And I think it just like that the quote from Donna Haraway of we have never been human. I think it was just really telling for me when I first heard that. It was like, what do you mean? Of course we're human. Like, and it's just like, oh, like what makes us us is not just the human cells in our body, but all of these other relationships, both inside of us and external to us, that allow us to kind of survive.
Great. Thank you, Andrew. Thank you so much.
Yeah,
It was
thank
wonderful.
you. All right. Bye, everyone. See you hopefully someday at the college.
Thank you very much, Andrew. Thank you, Jeff, for moderating this. Just a reminder to everybody, we usually post these for our faculty, students, and staff on our Hines Stream channel, which if you go to uh.edu/architecture/Hines Stream, you can find that tomorrow. Usually we live stream this to our Facebook page. Unfortunately, we weren't able to get that stream going today, so we'll also post the video to our Facebook page tomorrow. So thank you both. It was an absolute pleasure. And I hope everybody has a wonderful evening. Bye now.
Thank you.
Great. Thanks. See you later.